So we have a system as shown in this figure. We should find acceleration of the cylinder. So let's start with the free body diagram. Downward we have its weight, and we have a normal force, we have a tension in this direction, and we have a friction force. We should find direction of this friction force. We know that this cylinder can rotate only in this direction. There is no any other versions, there is no any other variants. So the contact part here with this inclined plane, with this surface, will be rotating in this direction, anti-clockwise. That's why friction force will be directed downward, basically, because cylinder is rotating upward at the point where we have a contact. Cylinder is moving upward, it means friction force will be directed downward. Here, at this point, we have a slipping because of the rope. Rope is inextensible. That's why here we have a slipping, sliding, because cylinder is moving upward. This point, bottom point, will be moving upward. That's why friction is downward, and the friction reached its maximum value. Coefficient of friction, which is K times normal force. Now let's apply Newton's second law for this cylinder. It will accelerate downward in this direction. Let's call it A. In this direction we have mg sine alpha. Also we have a friction force downward. Upward we have a tension minus should be equal to mass times acceleration. This is a Newton's second law. Resultant force equal to ma. We know that we already mentioned that friction force reach its maximum value. K times normal force. Normal force in this case, it's obvious, it's simple, mg cosine alpha. We can substitute it into this equation quickly, and let's see what we will see. K mg cosine alpha minus tension equal to ma. So this is a Newton's second law. At the same time, we have a rotation. Cylinder is rotating, so it means we can apply torque because it's rotating. It's rotating in anti-clockwise direction because of this tension. This tension is trying to rotate it in anti-clockwise. Friction force is trying to rotate in clockwise, so they are opposite. They have opposite torques, but torque of the tension is greater. That's why it's rotating in anti-clockwise. Tension times small r, its torque equal we are. So we are applying writing torque according to the center. So that's why we'll multiply by small r minus friction force times big R equal to moment of inertia of the cylinder about its center, which is I0 given times angular acceleration. So it is accelerating in this direction, rotational acceleration. And angular acceleration will be equal to acceleration A divided by small r, because this point where we have a contact with the rope is not moving. It's not moving, acceleration is there, 0. It's rotating around this point, basically. So now let's check how many equations we have and how many unknowns. This is equation number 1. We have a tension unknown and acceleration. This is equation number 2. Here we have also tension unknown and acceleration. It means logically we can solve this problem. 2 unknowns, 2 equations. Further is totally mass. We can do it very quickly. From this equation we can derive tension. Friction force times R, friction force K mg cosine alpha times big R. So tension equal to, we need to divide this part by small r. Now we can bring this tension into the first equation, and in this equation we will have only one unknown, acceleration. So let me copy equation number 1. Minus tension, which is this one. Equal to MA. Let me take this part to the right. So we have a kmg cosine here. We have a small mistake here, it should be minus. Yes, so let me take kmg cosine out of the bracket. So here we have 1, here we have minus big R over small r. Here we have MA plus I0A over R square, or we can write in this way, R square M R square plus I0. So A is unknown here. We can take mg outside. Mg, here we have sine alpha plus cosine alpha, 1 minus R over R. We need to multiply by R square mg R square and divide by this part. I0 plus mr square equal to A. So this is acceleration of this cylinder. So here we lost K. We have a K. So this is the final answer.